Namaste to everyone. Welcome to this lecture. Last lecture we looked at the idea of combining points and combining vectors, wherein we looked at the idea of linear dependence and linear independence among vectors which are in 2D, that means vectors which have two components. We looked at that and we asked a question. When we finished the lecture, we stopped the lecture with a question asking how do we get to all possible destinations, or can we get all possible vectors in 2D as a combination of as a linear combination of the linearly independent vectors. What happens if the vectors are dependent? So, we were trying to answer that question and we will take it forward from here. The agenda for this lecture is basically looking at the idea of linear independence and linear dependence and, of two component vectors, and we look at the angle between the vectors and then we go ahead look at the idea of orthogonal projections. So, let us go ahead. So, recall that if u and v are u is equal to u1 u2 and v is equal to v1 v2 are such that if v is equal to say some alpha times u, where alpha is some scalar, we said we called u and v as linearly dependent vectors. That means these are vectors which are parallel to each other, they are linearly dependent vectors. Else, if not, we call u and v as linearly independent vectors. We call u and v as linearly independent vectors. Now, let us take an example and then see what is it to obtain the linear combinations of linearly dependent vectors and linearly independent vectors. Let us consider a simple example where let me take u to be 1 0 and v to be 2 0. These are basically two vectors which, if you actually see on if you see, these are basically the vectors on the E1 axis, or the x1 axis, and this is basically the x2 axis. So, we see that the vector 1 0 is basically this vector, this is 1 0 1 2 3 4, let me do the 0 1 2 3 and 4. So, this is the vector u, and we wanted to look at another vector v. The vector v is 2 0, which is here, this is the vector v. Now, assume that I want a vector which is basically 1 2, this is the vector that I want. So, the question is, can we express w as a linear combination of u and v? Now, it is very interesting to see here that the vector u and the vector v, are along the same directions, and the vector w is in a different direction. Vector W is in a different direction. So, what are the vectors that we wanted? We want W is equal to 1 2. So, we want to look at W is equal to 1 2. So, the question is, can W be written as alpha 1 into 1 0 plus alpha 2 into 2 0, where W is equal to 1 2. 1 2 I do not know, we are going to see whether we can write this as alpha 1 into 1 0 plus alpha 2 into 2 0. Now, if we multiply the scalar and then check what happens, we get on the left hand side 1 2, which is equal to alpha 1 0 plus 2 alpha 2 0, which essentially means we have the vector 1 2 to be equal to alpha 1 plus 2 alpha 2, and the second coordinate is 0. It is very interesting to see that you may get, for different values of alpha 1 and alpha 2, you may get okay, let me put it this way. So, this is easy to understand. So, let me take this as alpha 1 into 0 plus alpha 2 into 0. Now, in the first case, if you look at the first coordinate, you could actually put some values of alpha 1 and alpha 2. For example, you put alpha 1 is equal to minus 1 and alpha 2 is equal to 1, I would get minus 1 plus 2, which is 1. So, the first coordinate is satisfied. However, if you put alpha 1 is equal to minus 1 and alpha 2 is equal to 1, you would still get a 0 in this, you will still get a 0 in the second component, which can never be equal to 2, which means you find that if you have two linearly dependent vectors, the resultant vector in this case, which is basically 1 2, you cannot obtain this as a linear combination of the vectors that are given to you, which is basically 1 0 and 2 0. Whatever that we try to do, even if you put different values of alpha 1 and alpha 2, sorry, alpha 1 and alpha 2, the product of alpha 1 with 0 and the product of alpha 2 with 0 is always going to give me a 0, and there is no way that I will be able to get the second coordinate 2, which means we clearly understand that if you have linearly dependent vectors, there is no way that you will be able to traverse to all the destinations in 2D, or there is no way that you will be able to get every vector in 2D as a linear combination of these two vectors, let us say 1 0 and 2 0. So, what is the moral of the story? The moral of the story is, if two vectors are linearly dependent, so let us write this, no way to get second coordinate 0, get second coordinate of 2, of W is equal to 2, as 2 is equal to 0 times alpha 1 plus 0 times alpha 2. So, if two vectors are linearly dependent, then there is no way to get all possible vectors, all vectors. Remember, we are just talking about 2D. I will just say in let us say 2D, and we assume that the vectors have only I mean we say that the vectors have only two components. If the two vectors in 2D are linearly dependent, then there is no way to get all the vectors as linear combinations of these two vectors. Right. So, that is the problem with linearly dependent vectors. There is no way that you will be able to get all vectors in a particular in this case, let us say in 2D, basically your xy plane, let us assume that it is x1 x2 plane. There is no way that you will be able to get the vectors, all the vectors as a linear combinations of two dependent vectors, linearly dependent vectors. However, so what we are going to say is, however, if vectors are linearly independent in 2D, we can get every vector as a unique linear combination of these linearly independent vectors. And we will see that this idea is what we call as the idea of basis when we look at vector spaces, where basis the linear combinations of the basis vectors will actually give you all possible vectors in that vector space and so on. Again, we will be dealing that in detail. So, the thing is, like, if you have let us say we will take an example here, example, let us take u to be the vector 2 1 and v to be the vector 1 2. Now, what we want, let us check, can let us say 4 5, let us say this, let us call this as the w vector, can w is equal to 4 5 be expressed as linear combination of 2 1 and 1 2. Now, what does that mean? I want to write 4 5 as alpha 1 into 2 1 plus alpha 2 into 1 2, where alpha 1 alpha 2 are real scalars. Are basically some real numbers. So, what do we get? We basically get 4 is equal to 2 alpha 1 plus 1 alpha 2 and 5 is equal to alpha 1 plus 2 alpha 2. From the knowledge of solving system of equations which we read in the previous lectures, we would be able to understand that I mean, this is a system of two linear equations in two unknowns. We will be able to solve this. If you solve this, we get alpha 1 is equal to 1 and alpha 2 is equal to 2, which means the vector 4 5, you can solve it and see, you can solve the system of equations. Solving this, we get alpha 1 is equal to 1 and alpha 2 is equal to 2. So, we get 4 5, which is nothing but 1 time 2 1 plus 2 times 1 2. Now, what does that mean? Again, let us see our geometrically, like, what does that mean? So, we have our x1 axis, we have our x2 axis, 1 2 3 4 5 6, 1 2 3 4 5. So, we have 1 2 3 4 and 5, 0 1 2 3 4 5 6. Now, let us take the vector 1 2 2 1, 2 1 is basically this vector. Then let me take the vector 1 2, 1 2 is basically this vector. Now, what it says is 1 time 2 1 plus 2 times 1 2, 2 times 1 2, if I were to take 2 times 1 2, this is going to be 2 4. So, 2 times 1 2 will go here 2 4. I can do the parallelogram law of addition by basically either taking this, drawing this vector parallel here, or probably drawing this vector parallel here. So, we get into the we get to 4 comma 5, which is basically here. So, let us see how that happens. So, I am going to draw this vector parallel 1 2 here, that is 1 2, and so you could see that 2 1 1 2 I mean 2 1 I have drawn parallel, then again I go here, and that is exactly where they meet, and this is the resultant vector that we have. So, this is 1 time 2 1 and this is 2 times 1 2, and that gives me this vector which is basically my 4 5. That is the vector which is basically my u1 u, v and w. So, let us mark that. So, we have this vector which is basically the u vector, and this vector is 2 times v vector, and that vector we are going to have as the w vector. This vector is my w vector. Yeah. So, you can solve it like a system of equations, and then you can actually get the values of the scalars, and if there is a scalar exists for which you can get the resultant vector this way, then you have the vectors to be the resultant vector to be expressed as the linear combination of the other two vectors. Okay. Now, the question is, how do we figure out whether the vectors are linearly independent or dependent? That means we already know the idea that if the vectors are parallel, then you are going to say that I mean you are going to talk in terms of angle. You can talk in terms of angle. If the vectors are going to be linearly independent, then we know that the vectors are going to be, I mean there is going to be some angle other than 0 degrees which is formed between these two vectors. The angle between the two vectors is something greater than 0 degree. So, how do we figure out if the vectors are going to be linearly independent or not? At least two vectors in, let us say 2 dimension. We are going to say two component vectors, we are going to look at them, and then we are going to figure out whether the vector is going the two vectors are they could enclose a parallelogram, which means they are going to be a linearly independent set of vectors, or they are just going to be along the same straight line passing through the origin and the corresponding point. So, the idea is how do we get to know. So, for that what we do is we get into the notion of dot product, and we get into the idea of the angle between the vectors. So, we are going to look at the notion of dot product. Now, this is something all of us would have learned, but then let us actually get into the idea of vectors. Why would we want the dot product? So, let us assume that we have two vectors, let u and v be two vectors, be two vectors. I mean all the vectors that we consider here are basically two component vectors which are therefore there in 2D. So, we are going to just look at the two vectors, let u and v be two vectors. So, the questions that we want to ask is so what is the question that we want to ask? We want to ask like, are u and v, the easiest thing to figure out is, are u and v orthogonal to each other? Orthogonal to each other, are perpendicular to each other, right, or perpendicular to each other. If they are perpendicular to each other, we know that cos 90 is 0. So, that is going to I mean that is going to tell us that, I mean you look at some idea of cos theta, and that is going to tell us that look if cos theta is 0, then the vectors are perpendicular. B, angle between them. So, what is the angle between u and v? And C, we are going to ask, are the two vectors the same vector? What do we mean by that? Are the two vectors the same vector? So, what do we mean by that? That means the angle between them is 0. That is what we are going to look at. So, in order to find out this, let us first of all look at a simple case where I have this vector, let me call this as vector u, and let me call this as the vector v. I call this as vector u and that vector as the vector v. Now, what I do is you can always do this, you can drop a v which is parallel to it, which is basically placed at the arrowhead of the u vector, and this is going to be my resultant, which is basically my vector u plus v, and this is the vector v. This is the vector v. Now, you note that in this case you already know that the angle between them, it is a right triangle, the angle between the two vectors u and v is 90 degrees. We want to establish what is the condition for the two vectors to be orthogonal. How do we get it in terms of the knowledge of the vector operations and stuff. Okay. So, what we do is note that we can actually use the idea of or Pythagoras theorem, where we are going to say u plus v the whole square. If you take, that means the length of this vector hypotenuse square is basically the length of adjacent square plus the length of the opposite square. So, what are we going to do? We are going to say that the vector u is basically defined as two component vector as u1 u2, the vector v is basically v1 v2, and the vector u plus v is equal to u1 plus v1 u2 plus v2. Yeah. So, we already have seen the notion of the norm or the length of the vector in the previous class, where we said that the squared length of this vector is basically the sum of squares of the components. So, what we are going to have? We are going to have u1 plus v1 the whole square plus u2 plus v2 the whole square is equal to u1 square plus u2 square plus v1 square plus v2 square. Now, if you do the expansion of this bracket, you get u1 square plus v1 square plus 2 u1 v1 plus u2 square plus v2 square plus 2 u2 v2 is equal to u1 square plus u2 square plus v1 square plus v2 square. And you can knock off a lot of fellows here. u1 square gets knocked off, v1 square gets knocked off, u1 square and v1 square get knocked off, u2 square and u2 square get knocked off, v2 square and v2 square get knocked off. So, what we have is 2 u1 v1 plus 2 u2 v2 is equal to 0, which implies u1 v1 plus u2 v2 is equal to 0. So, what are we going to say? We are going to say that if the vectors are perpendicular, if we have already told that these two vectors are perpendicular here, if u and v are perpendicular, then if u and v are perpendicular, then the sum of products of their components, right, component wise products, the sum of them is basically the it is equal to 0. Then we are going to say that then the sum of product of their components is 0. Which we capture in a short form as u dot v is equal to 0, where we already know that u is basically this vector u1 v1 u1 u2 and v is this vector v1 v2, and what it says is u dot v is equal to u1 v1 plus u2 v2 is equal to 0, and it is interesting to note that if you have a vector u. So, let us make a comment here. So, let us do this note. If u is equal to u1 u2 is a vector, and we want a vector orthogonal to u or perpendicular to u. We want a vector perpendicular to u. It is very clearly, I mean, one can very clearly see that we want a vector, let us say v, which is perpendicular to u. Then we know that u1 v1 plus u2 v2 is equal to 0, which implies my vector v is nothing but minus u2 u1. So, what do we get? If it is minus u2 u1, I get u1 into minus u2 plus u2 into u1, that is equal to 0. Is that okay? So, that makes sense. So, you get the idea of orthogonality, I mean you get the idea of perpendicular vectors, and the dot product, it returns a number like what you see here. So, the dot product basically is also called as your scalar product. The dot product returns a number. A scalar, and therefore, you also call this dot product as the scalar product. And it also goes by the name inner product. It is also called as the inner product of two vectors, okay, the inner product of two vectors. So, if you see in the matrix form, you have this vector u basically, which is a 2 component vector, or I will call this as a 2 column, it is basically a 2 by 1 matrix, and v is also a 2 by 1 matrix, v1 v2 is also a 2 by 1 matrix. So, what we want is u dot v, which is basically given by u1 v1 plus u2 v2. We can clearly see that this is matrix product done this way, u1 u2, you convert that column vector that you had, which is u with the column matrix that you have, you convert that to the row matrix by taking the transpose. So, I am going to get u1 u2 into v1 v2, which is equal to u dot v. So, what am I going to do? I am going to write this as u transpose v. U dot v is u transpose v. What is interesting is u1 v1 is the same as v1 u1, u2 v2 is the same as v2 u2. So, I am also going to write this as v transpose u, which is also the same as v dot u. Is that okay? So, that basically tells me that if the dot product is 0, if the vectors are orthogonal or perpendicular, if the vectors are perpendicular, then the dot product between them u dot v, or the, which is also the inner product of the two vectors u transpose v, which is the same as v transpose u, which is the same as v dot u, that must be equal to 0, right, that must be equal to 0. So, the question is, okay, we figured this out, that if the vectors are orthogonal, the dot product must be 0. Now, we want to find out what is the angle between the two vectors. How do we go to the idea of getting the angle between the two vectors? and that is exactly what we want to look at. We will look at the angle between two vectors. So, how do we find the angle? So, let us ask this question: how do we find the angle between two vectors? If the angle between the vectors is 90 degrees, then v dot u is 0, or if v dot u is 0, then we say that the angle between the two vectors is 90 degrees. But I want to capture the idea of I mean any general angle, not very specifically 90 degrees. I want to find out for any angle theta, how are we going to capture this notion of this angle between two vectors mathematically. So, how do we find the angle between u and v? Is there a way to find out? If that is the case, how is it going to be I mean what is going to be the mathematical expression for finding out the angle between the two vectors. So, what we will do is having studied the dot product between the two vectors, the necessity came up from finding out the angle between the two vectors, because we wanted to figure out if two vectors are given, are they linearly independent or dependent. If they are along the same direction, then the angle will be 0. If they are going to be in different directions, then it is going to have some different angle. So, in the quest for finding out whether the vector is linearly the two component vectors that we have is I mean they are linearly independent or not, we were actually trying to look at the angle between the vectors. And so, the easiest was to find out to figure out what is the condition for two vectors to be perpendicular. We figured out that two vectors can be I mean two vectors are said to be perpendicular or orthogonal whenever this happens. So, whenever the sum of the products is 0, whenever u dot v is 0, that means component wise products, add them, the sum of the component wise products must be 0. So, that is what we did. In the next lecture we will look at the angle between the vectors u and v. Thank you.